In the last lecture, we were introduced to the concept of momentum. Here, given the symbol p, a vector quantity which is equal to the mass of an object multiplied by its velocity. It's really important to remember that momentum is a vector, because we just finished working with kinetic energy and potential energy. Those are not vectors. They don't have a direction. But momentum has a vector by virtue of the fact that it's defined in terms of the velocity. When an object is moving in the positive direction, it has positive momentum. And when an object is moving in the negative direction, it has negative momentum. The idea of momentum came from Isaac Newton. It's the quantity of motion. It's the amount of motion that an object has. So we rewrote Newton's second law in the context of momentum, where the net force, instead of being equal to the mass times the acceleration, is set equal to the change in momentum divided by the time in which the momentum changes. Now, that hasn't changed Newton's second law at all. It's just a different way of looking at Newton's second law. A little rearrangement of that gave me my impulse force law, which is that the change in momentum delta p, which we sometimes refer to as impulse, is equal to the net force multiplied by the time in which the force is applied. So this is a new way of looking at Newton's second law, and you'd be right to wonder at this point, why do I need a new version of Newton's second law? He's perfectly happy with the old version. Well, just like applying Newton's second law to work and energy, we'll discover that the application of this version of Newton's second law to the solution of fundamental problems is going to reveal a new symmetry of nature. That there's actually another hidden truth, if you will, behind these equations. In all of the physics that we've done so far, we've considered individual objects. When I do kinematics, I look at the position, velocity, and acceleration of an individual object. When I apply Newton's laws, I draw a free body diagram for an individual object. I even consider, in most problems that I solve, the total mechanical energy of an individual object. What I haven't considered thus far, and what is extraordinarily important to my understanding of the way my universe works, is how do objects interact one with the other? That is, two objects considered at the same time. Any two objects in my universe in proximity to each other exert forces one upon the other. Even if they'd ever make contact, they exert gravitational forces, or perhaps electrodynamic forces, forces unseen. Nevertheless, when one object interacts with another, there are forces, according to Newton's third law, that one acts upon the other, and it's those forces that I seek to investigate. I'll begin by considering the simplest possible interaction that I can imagine. Here I have two objects, A and B. They have masses, and that's going to become interesting to me, but for the moment I want to consider these velocities that they have. A has a velocity VA, which is directed to the right. We might call that a positive velocity. And B has a velocity VB directed to the left. I would call that a negative velocity. Now, I'm not implying anything about the magnitude of those velocities. They could very well be different. I'm not implying anything about the masses. They could very well be different. But there's no doubt about it, in the seconds to come, A and B are going to collide one with the other. A collision is the simplest way that two objects can interact one with the other. Now, when a collision takes place, there are forces that are exerted according to Newton's third law. Newton's third law, which we didn't make a lot of very explicit use of when we did Newton's second law, we just sort of keep it in mind that action-reaction forces exist. Newton's third law plays an important role here. When I realize that A comes in contact with B and they exert forces of contact. Now, the nature of those forces, I'm not interested in at the moment. Perhaps it's like springs, perhaps it's electromagnetic, gravitational, whatever. There are forces of interaction. But in the third law, Isaac Newton tells us that these forces are equal and opposite. So I've drawn them here, two vector forces in opposite directions. And I've labeled them in a sensible way. On the left, pointing to the left, I've drawn the force that B exerts on A. So that's my notation there with the subscript, B exerted on A. On the right, with a force directed to the right, I have the force that A exerts on B. And I'm going to proceed from the proposition of Isaac Newton that these two forces must be equal and opposite. I can write that as an equation. Here, the force that B exerts on A, which I've written as a vector, you can tell because I've written a harpoon on top of it, is equal to negative the force that A exerts on B. Again, a vector. The negative sign implies that they are equal in magnitude but opposite in direction, exactly in accordance with Newton's third law. Now, I have a new version of Newton's second law that I'm going to apply here. A version of Newton's second law that says that the force that B exerts on A will change A's momentum in a certain quantity of time. So the force that B exerts on A, written here on the left-hand side, can be written as the change in momentum of A divided by the time in which A's momentum changes. On the right-hand side of the equation, the negative of the force that A exerts on B can be written as the negative of the change in B's momentum divided by the time in which B's momentum changes. A natural observation that I would make at this point is that the change in momentum of A and the change in momentum of B happen at the same time. That is, on the left-hand side of the equation and the right-hand side of the equation, the delta t's are the same and they can be canceled, so that the change in momentum of A is equal to the negative of the change in momentum of B. What that means is that if the momentum of A increases, the momentum of B must decrease by exactly the same amount. And if the momentum of A decreases, the momentum of B must increase by exactly the same amount. Now, I'm sure this isn't a big spoiler, but what that sounds a lot like to me is a law of conservation, that the momentum is being exchanged from one object to the other. A gives up momentum and B receives it. B gives up momentum and A receives it. Those two changes being equal and opposite. The change in momentum of A and the change in momentum B are like any other change quantities that we've encountered in physics. They're final minus initial. So I can write the change in momentum of A as the final momentum of A minus the initial momentum of A. Notice once again here that I'm using the prime notation to indicate the final value and the unprime notation to indicate the initial value. So the change in momentum of A is PA prime minus PA. And again, on the right-hand side, the change in momentum of B is equal to the final momentum of B, PB prime, minus the initial momentum of B, PB. A distinct difference that I can see on the left and right-hand side of this equation is the negative sign that appears on the right. I'm going to do a little bit of an algebraic trick, and on the right-hand side, I'm going to absorb that negative sign into the quantity. If you remember your algebra well enough, you'll realize that what this does is reverse the order of the difference quantity on the right-hand side, so that it becomes PA prime minus PA is equal to PB minus PB prime. So here I have an equation with the difference in the A momentum on the left-hand side and a difference in the B momentum on the right-hand side, and that's perfectly fine. But what I'd like to have instead is I'd like to have an equation that has all of the initial momentum on one side of the equation and all the final momentum on the other side of the equation. I can achieve this, looking at the first equation here, simply by adding PB prime from the right-hand side to the left-hand side and adding PA from the left-hand side to the right-hand side, resulting in PA prime plus PB prime is equal to PB plus PA. Everything final is on the left-hand side, and everything initial is on the right-hand side. My next step is a simple one, but important in the context of our thinking. All I'm going to do is take this first equation here, that is final on the left-hand side and initial on the right-hand side, and flip it, so that as I read the equation from left to right, I'm reading from initial to final, the same way I organized energy. When I talked about the law of conservation of energy, I wanted to consider first the initial energy of the system and then later the final energy of the system. So my equation is written chronologically. And that's what I've done here. I have all of the initial quantities on the left and all of the final quantities on the right. Now, on the left-hand side of the equation, I have the initial momentum of A plus the initial momentum of B, which is a quantity that seems very much to me to be the total momentum at the start before the collision happens. And on the right-hand side, I have the momentum of A after the collision plus the momentum of B after the collision. I mean, it seems to me that that seems an awful lot like the total final momentum. That, of course, is exactly what I'm getting at. The total initial momentum of the collision, the total initial momentum of the system, and by the system I mean object A and B considered together. The total initial momentum must be equal to the total final momentum. If I call the total initial momentum just P, and the final momentum P prime, I can express this equation as P is equal to P prime. What I've discovered here, what I've realized, is that the total momentum is a conserved quantity. It's important to point out that the momentum of A changes during the collision. The momentum of B changes during the collision. The important point is that the total momentum is a number that does not change. It's like saying that during the motion of a physical system, the kinetic energy changes and the gravitational potential energy changes. Perhaps the kinetic energy decreases and the potential energy increases. Nevertheless, the total energy of the system may be a conserved quantity if there's no work done by outside forces. Well, here, the total initial momentum is equal to the total final momentum. So what I've stumbled upon here, just by applying Newton's second and third law to the collision of two objects, A and B, the one to the other, is a fundamental law of the universe, the law of conservation of momentum. When a physical system of multiple objects interacts, the total initial momentum before the interaction is equal to the total final momentum. Now, when you do that, you have to be careful, because unlike energy, which is a scalar quantity, momentum is a vector. And so in one dimension, momentum can be positive or negative. So how you calculate the total initial momentum needs to be done with a bit of care, because some momentum can be positive and some momentum can be negative. For example, how we got here, A's momentum was positive and B's momentum was negative. Nevertheless, the law of conservation of momentum applies to the interaction of any two objects, and as it happens, more than two objects in our universe, under the action of mutual forces commensurate with Newton's third law. Now, at this point, you might say, well, hang on a second, there's a bit of a cheat here. The situation that we just solved is a very simple one. You have A acting on B, and there are only two forces. And those forces are very, very simple. Would this have worked out in a more complicated situation? Well, the answer is yes. In fact, consider this. If object A and object B were instead automobiles, when they collide the one with the other, the forces are extraordinarily complicated. Imagine drawing a free body diagram for that. Nevertheless, oh look, watermelons. Nevertheless, every force that acts in this collision is an action-reaction pair. There may be thousands, but every force is action-reaction. So even though in my initial assumption, which was A and B colliding together and the forces were simple to understand, it doesn't matter if I had more forces, because ultimately the assertion that I'm going to make is that all of those forces are action-reaction forces. And since Newton's second law says the net force, sigma F, equals ma, then the total force will always add up to zero. We could have come to this conclusion immediately just by looking at Newton's second law in its momentum form. Here, the change in momentum is equal to the net force multiplied by delta t. When I consider two objects, like A and B, or like two automobiles, or a planet and a comet, whenever I have two objects interacting one with the other, the forces are always action-reaction. No matter how many forces there are, or no matter how strange the nature of the forces are always action-reaction. That means on the left-hand side, or pardon me, the right-hand side of this equation, sigma f, the sum total of the force of interaction, will be 0. And that means that the change in momentum must be equal to 0. The law of conservation of momentum. Now, to be clear, the momenta of individual objects may change during the collision. It is the total momentum of the system that is the conserved quantity. Armed with the law of conservation of momentum, I now want to solve a few examples just to see how this law of conservation of momentum is going to manifest itself in real problems with real numbers. To do that, I have this simulation where I'm able to create these two objects, Object 1 and Object 2. For the moment, I've given them the same mass. Object 2 is sitting at rest. Object 1 is moving along with a velocity v that I choose, and I've chosen it to be 1 meter per second. And so in this initial condition that I've shown here, there is some momentum. Object number 2 has no momentum by virtue of the fact that it has no velocity, but Object 1 has a mass of 0.5 kilograms and a velocity of 1 meter per second. That means it has 0.5 Newton seconds of momentum. Object 2 has 0 Newton seconds of momentum. So my expectation is, after this collision occurs, that the total amount of momentum will be the same as the initial momentum, 0.5 Newton seconds of momentum. So I'll run this simulation and we'll see how it plays out. Kind of a remarkable thing happens. I see Object 1 comes completely to rest, and Object 2 moves along with exactly the same velocity that Object 1 has. Inspecting the momentum here, I find now that Object number 1 has no momentum, and Object number 2 has 0.5 Newton seconds of momentum. That is, all of the momentum of this collision has been transferred from Object 1 to Object 2. We'll discover by solving lots and lots of problems and looking at the general behavior of these systems that this is a consequence of the fact that the two objects have the same mass. There's another secret consequence hiding in here, but I'm waiting for another lecture to get into that one. I'm going to restart the system again, resetting it back to the way that it was, but I'm going to change the mass of Object 1. I'm going to make the mass of Object 1 only 1/4 of a kilogram, that is 0.25 kilograms. I'll leave its velocity the same. Because I reduced the mass, the momentum has also reduced. The total momentum of the system, Object 2 has no momentum, Object 1 has 0.25 kilograms multiplied by its 1 meter per second velocity is 0.25 Newton seconds of momentum. We'll run the simulation and see what happens. Here, a more interesting result than the first example. Object 1 collides with Object 2 and completely turns around and heads in the opposite direction. This is typical of collisions where the colliding object, Object number 1, is less massive than the object that is struck. And if you take a moment to ponder it, you'll realize that this matches your expectations from real life. Their velocities have both changed. The velocity of Object 1 was 1 meter per second. Now it's negative 0.33. The velocity of Object 2 was 0. Now it's 0.67. So the velocities have all changed. But let's look at the momentum. The momentum of Object 1 is now negative 0.08. It's important to appreciate momentum is a vector. Since Object 1 is now traveling to the left, the direction we presume to be negative, it has a negative momentum. Object 2, which had no momentum before, now has a momentum of 0.33. Our initial momentum was 0.25. So what's going on here? Well, it happens that 0.08 plus 0.33, some rounding occurred on there, it's going to add up to 0.25. The total momentum before and after collision are the same. Momentum is conserved. I'll reset it again, but this time I'm going to make the mass of Object 1 1 kilogram. I wonder if you can anticipate what's going to happen. Now Object 1 has the larger mass of the two. And so I run the simulation and I discover, perhaps what you expected, that Object 1 continues moving in its original direction but its velocity is reduced. Object 2 is now moving to the right with a very large velocity. I neglected to look at the total momentum before the collision, so I'm going to drive it back and restart it. The total initial momentum was 1 Newton second of momentum. And then I run the simulation, and I discover after collision that the final momentum is 1 Newton second of momentum. So I could play with this simulation all day, choosing various combinations of masses and velocities. And what I would find in each case is that the total initial momentum of the system is always equal to the total final momentum. In order to apply the law of conservation of momentum to the types of problems that students have to solve in their physics homework, you need to be able to calculate what is the total initial momentum and the total final momentum. I find that the easiest way to do that is to write the law of conservation of momentum as a standard equation for the interaction between two objects. Here it is here, the last equation on the screen, where I've written the total initial momentum as the sum of the momentum of two objects that are interacting, the one with the other, MAVA plus MBVB. Notice that I have harpoons on VA and VB. They are vectors. So I've written a plus sign here, adding these two momenta together. But of course, in any situation that I find in problem solving, it's possible that one of the momenta could, or both, could be negative. It's also possible that A or B could have zero velocity to start with. Well, that's okay. It simply means that one of the objects has momentum and the other doesn't. On the right-hand side of the equation, I have the total final momentum, MAVA prime plus MBVB prime. The total final momentum. Again, vectors, possibly positive, negative. But just like I use my law of conservation of energy, where the initial energy plus or minus any work that is done is equal to the final energy, I use this version of the conservation of momentum at the start of every problem, filling in all the numbers where they're appropriate and then doing whatever algebra is necessary to find the unknown thing. Try to appreciate here that the advantage is that when two objects collide, one with the other, the forces between them might be extraordinarily complicated or unknown. But this equation doesn't require me to know the nature of the forces of the interaction. I don't have to know anything about it. The law of conservation of momentum and the fact that momentum is a conserved quantity gives me leverage to solve problems whose details are either not understood or impossible to understand. And so my ability to understand the nature of my universe has been expanded.